Alright, welcome back from lunch. So we're here for the second part of the Differential Privacy and Statistics mini course. So Gautam Kamath, who's a fellow here with us, will talk about sort of the theoretical computer science perspective on the materials that I talked about. And since he's here all semester, we can hopefully set up a discussion that will last a while.
Thank you, John. Thank you, John and Adam, for inviting me and also for their valuable feedback on this talk. So today I'm going to give you, maybe this should not be a TCS perspective, that's rather very broad, at least it's my perspective as a theoretical computer scientist. In this talk I'll be mentioning things that's sort of from a TCS or a statistics perspective. Let me note that there's other players in this game who implicitly work maybe in one or the other, including information theorists and machine learning. But just to keep it simple, I'm going to refer to statisticians and theorists, maybe as very broad generalizations. Okay, the structure of this talk will be roughly as follows. In the first part, I'll describe our setting, the type of goals we focus on, maybe a little bit more philosophical in some sense, like why do we care about these problems. The second and third part, I'll go more in depth on specific applications, including hypothesis testing and distribution estimation. And then in the last part, I'll just mention a few other problems which have been studied as well. And if any time anything's unclear, of course, feel free to ask. This can be as interactive as you want. Okay, so let's start off by just seeing the difference between algorithms versus statistics. In the very classical algorithm setting, what we would imagine is we have some sort of data set, x1 through xn. This is fed into some algorithm m, and we achieve some sort of utility based on how accurate our answer is, y, with respect to the original data set. So this is a bit abstract, but this is kind of like a very static. There's some given data set, and you want to infer something about it. However, I usually picture statistics as being a little bit different. So we have the same sort of data. We run an algorithm on the data set, of course. But the target isn't really a utility with respect to the data set. The target is really utility with respect to some unknown sampling distribution. So now the picture is like as follows. You have a distribution P, which is unknown. That distribution generates some data set x1 through xn. Then you feed that data set into an algorithm, which will give you some output y. And the idea is you get a utility derived on it's some function of the original distribution and the output. Essentially, you want to approximate the original distribution, not the actual data set. That's clear. So this is the general setting we're going to focus on, and we have two main desiderata. The first desiderata is kind of the non-private guarantee. We want, first of all, of course, in any setting that our algorithm is accurate. In this case, we're going to have it be a stochastic guarantee. Stochastic in the following sense. We want our algorithm to be accurate with high probability over the data generating process. In the sense that, if you're sampling from a distribution, there's always some randomness and wacky things could happen. But assuming not too wacky things happen, we want our algorithm to be accurate. And in particular, this may require certain assumptions about our generating distribution to hold. For example, we might require it to be Gaussian or from a multinomial or something like that. We'll revisit this a few times during the talk, and so it'll become more clear, perhaps, what I mean by assumptions. But the other requirement is privacy, which we want always. So that is, for any sort of realization of the data set, we really want to make sure the algorithm is private, no matter what sort of low probability events happen. Yes?
So by algorithm is private, do you mean that the outputs are private? Or do you mean that the algorithm is privacy preserving? Or do you mean it's closed source and I don't know what's in it?
It's pretty much in the same setting. Like if you just sort of ignore the distribution P, we're going to say that essentially if X is our data set, then the output of mx is private in the usual sense we've been referring to so far. I'll define it in a few slides, but yeah. Essentially, just think about it in the same way we've used it in all the other talks so far. But it's especially key that for any possible input that is private. And we'll do a bit of philosophy about this in a few slides. And in this talk, I'll pretty much always be using epsilon differential privacy, except noted otherwise. But really, I don't want to get too much into the weeds about epsilon versus approximate differential privacy. This thing's privacy. Any questions about the broad? Yeah, Prashant?
Why is it always private? Is that important?
Yeah, and we'll revisit that in a few slides. But just to sort of show you, I guess, these two desiderata, the type of inputs and what might happen, imagine, for example, we want to run a private algorithm on some data which is Gaussian, in the sense that we sort of assume the underlying distribution is Gaussian. So I generated some sample from a Gaussian distribution. In this case, we want our algorithm to be private, and we also want it to be accurate. But let's suppose, we get our data set, but it isn't actually Gaussian looking. It looks something more like this. So, this doesn't obviously look like a Gaussian to anyone. But even in this case, we still want to be private, though we may not have the utility guarantee for our algorithm. So hopefully that's clear. Let's revisit this question that Prashant asked. Why worst case privacy? Well, there's a few different reasons why you might want worst case privacy really over any data set. And one reason is that you could violate privacy of outliers, in the sense that if you have one data point which lies far outside what you'd expect, then maybe it might not. You still want to maintain their privacy. Like, let me give you an example to make it a bit more concrete, perhaps. Imagine you had a salary data set. That is, all the employees who work at a company, you get their salaries, and you want to somehow privately output some statistic of this data set. For example, maybe the median salary. One possible way of doing this is appropriately noising the data set and then releasing that noised data set. So let's take a look. Here I generated a bunch of numbers which are sort of centered at $65,000, which is perhaps a salary. And you can see that I noised it. And now this noised data set is somehow, it looks kind of, believe me when I say it's private in this case at least. And it looks like sort of, sure, this is noised. But let me say, what if there's an outlier? What if your data set, has, say, a manager or some higher up who makes a lot more money than everyone else? Then if you do the same type of noising, then you get this individual out here. So you can see, like, he makes still about $300,000. What this example is meant to convey is that while in the left setting, while sort of we know the data is well concentrated and noising it would preserve privacy here, in this case, where we might have an outlier, we did not preserve the privacy of this individual. And so this is the type of thing we generally want to avoid. I mean, maybe you can make some argument about how capitalism is evil and we should identify this individual, but that's perhaps a discussion for this evening. So yeah, hopefully this convinced you that an individual's privacy could be violated as a result of being an outlier. And another reason perhaps is that statistics can be retracted, but private information can't really be retracted. This is something that Kobe mentioned yesterday, like a post-privacy world, in the sense that, for example, it's not uncommon for, I think it's somewhat uncommon, but it's not unheard of for there to be publications saying that like this study has been falsified, it wasn't able to be reproduced, whereas once you tell someone something that's private, there's no real going back from that. So perhaps we want to be a bit more conservative. Yes?
So if you go back to the previous slide,
This.
Yeah, so is that, is the outlier's privacy being violated or is the utility being violated? Because presumably that orange thing is the noisy data that you release.
Yes.
Right? And so I don't see any orange around that person. And so it sounds like you would just kind of not have that person at all, which would affect your utility, but not your privacy, right?
Right, so I actually didn't, like, what we can do here, like, the idea is we want to compute the median in some way. And one possible way is sort of noising the data set and then releasing it, and then on this released data set to compute the median. I claim that the median should be roughly the same for both these data sets after noising. But if we sort of release the data set early, then it would, before computing the median, then it would still violate this individual's privacy. Does that make sense? I'm saying that if you wanted to, say, privately release the data set, forget about any particular statistics, then the one on the left would seem to maintain privacy, but the one on the right identify that someone has a very high salary in this data set.
So there is noise around the outlier too?
Yeah, there is noise, but it's of a much smaller scale because, it's of the same scale, but it doesn't move him or her that much.
Oh, okay, because I couldn't see that, so I thought that was just kind of ignored. And
right, no. Believe me, there is noise added, but it's of a fairly small scale, which doesn't show up well here. Cool, thank you. Okay, and what sort of privacy guarantee do we want? Well, this is about differential privacy, so we want differential privacy. Let me just state in one sentence in case this is the first time you're seeing it again. Essentially, on two data sets which differ in only one entry, then you want the probability distribution of your algorithm to be very similar. So this is a bit of a mouthful, and we won't actually need it for today too much. The thing that I will refer to back and forth a few times is the idea that less sensitive statistics will be cheaper to privatize. This maybe you've heard before, but let's try to make this a little bit more precise. We're going to be trying, in general, to compute some function f. And the sensitivity of f can be seen as the maximum difference on neighboring data sets. In other words, if you take x and then you change one data point in x, either add it or remove it or replace it in some way, and you take the difference between the function value on those two data sets, then take some norm of it, I won't go into which one, this will be the sensitivity, the most it can change. This might be familiar to a lot of you, so I'm just going to, in case that didn't make sense, just let's say sensitivity and privacy are somehow related here. And the next thing I want to talk about is what we mean by utility. This will generally be a problem-specific thing, whether we're doing hypothesis testing or distribution estimation. But the general statement which we're going to be trying to understand is how much data is needed to approximately infer a property of the underlying distribution P with high probability. This is a very broad question. I'll be more precise in a bit. And if you ask where this question comes from, perhaps statisticians would point to this person, Carl Pearson. Carl Pearson was alive at about the year 1900, and he was a very respected and impressive statistician. He's famous for a number of things, including, say, the methods of moments, the chi-squared test, and unfortunately also racial eugenics. That's a bit of a footnote. But let's say within theoretical computer science, at least, the person who I often consider to be at least the father, in more ways than one you'll see, is Les Valiant, who introduced probably approximately correct learning in 1984. And at a general level, PAC learning is concerned with statements of the following form. Now, this is rather mathematical, so let me try to actually walk you through what this type of thing means. So the first segment of this, with n samples, we're going to try to understand how much data is needed. And I did n sub f, gamma, and alpha, which means that the amount of data we need will be a function of what type of problem we're trying to solve. Okay, so that's the data that we need. Now let's take a look at this term inside the probability. We're going to say that mx, which is the output of the algorithm, its difference with respect to the function on the unknown distribution is less than gamma. So it's saying that it's accurate up to accuracy gamma. And then when we wrap in a probability, we want this to be correct with probability at least 1 minus alpha. So just to sort of repeat this in sort of plain English, we want that our algorithm will give an output which is gamma accurate at least 1 minus alpha of the time, or it's approximately correct probably, which is where the name comes from. Are there any questions about this type of about this? Good. Perhaps this is familiar for some. Okay. So a running theme through this talk is understanding the cost of privacy, which is asking essentially how much more data is needed to guarantee privacy. Of course, pretty much all of the problems I'm going to mention are going to be things that we understand very well non-privately, but we want to understand really this additional cost due to privacy. So in particular, I will often write sample complexities as a sum of many terms, and often the first term will be the non-private cost, that is the sort of baseline as what we have to pay. And the question is, how big is this additive term, and in what situations is the private cost much, much larger than the non-private cost? Good. So one thing that's sort of a terminology thing that sometimes is a bit of has a bit of friction between statistics and computer science is what it means to be asymptotic. So let me sort of define two meanings of what it means to be asymptotic, and we'll see hopefully how they sort of refer to different settings. One is asymptotic settings, or asymptotic statistics. This is, Sesha mentioned this during her talk in the morning, but these essentially give guarantees when the sample size approaches infinity, as in, as our data set grows increasingly large, approaching infinity. So the most common example of this that you might have heard of is the central limit theorem, which in its sort of basic state is an asymptotic statement. Here's another example, which we'll see in a few more slides. We're going to say, like, as the sample size approaches infinity, we'll say some statistic will converge in distribution to, say, a chi-squared distribution. So the sort of main thing about this that I want to get across is it doesn't quantify the error for any finite n, but it says it's sort of in an asymptotic setting. This error goes to 0. On the other hand, asymptotics are also highly used by computer scientists, but perhaps in a slightly different meaning. In the sense, I usually mean big O notation. I mean big O notation when I mean asymptotics, which hide constant factors in lower order terms. And as an example, we're going to see to achieve accuracy, blah, 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 we require n equals O of this many samples. Now, what that really means is what it really means is something a bit technical, but this can often be read as the following, that we require n to be greater than c times this many samples for some constant c. Now, this constant c is often not specified, but that's often just due to a function of being perhaps lazy rather than it being sort of impossible to calculate, or also just to simplify the results in the sense the statement.
The case where it's easy to calculate but embarrassingly large.
Yes, that's often the case. So often computer scientists will state results up to like these constant factors and not show them. And I think one really good question is asymptotic optimality good enough? It's interesting because I think statisticians often fall on either side of this in the sense that let me just say computer scientists often asymptotic optimality is good enough. Give me a rapid and a big O and I'm happy. Whereas statisticians often like to either have asymptotic results, or if they're doing minimax results, as these sort of finite sample guarantees are called, they really want the right constants. As Sesha mentioned in her talk, this is often very important to get practically useful confidence intervals and things like that. So I think it's kind of interesting sort of culture thing.
So I mean, is it fair to say that in the stuff on the left that you don't know what the convergence rate is, you don't know when the convergence starts becoming good? Because you're saying on the right that we hide the C, but we know it. I feel like maybe that's not really a fair comparison. I think of the stuff on the left as being you ignore low order terms, but you worry about the leading constant.
I guess
don't worry about the leading constant either.
I've seen some things of the statement like that this converges to the right answer like as n approaches infinity, but what this kind of hiding to me in these settings has been like that the sample complexity is exponential in the dimension, which is something that I would prefer to understand better.
And we do that too with big O, right? Like for constant d, this is big O, blah.
Right, okay, but
if d is a relevant parameter, then it should be included in the big O.
Of course.
Yeah.
It kind of depends on the community. Like, say, people doing two-dimensional geometry, or like hide
the dependence on 2.
Finite dimensional geometry. I don't know, whatever.
Yeah. At least my personal taste, I like to understand, and if it's a parameter, even if it's exponential, I'd like to know that. But it depends indeed on the community. Cool. And I think this might.
So just going back just a little bit.
Yeah.
I mean, my interpretation of this actually is more that when you say that this is asymptotically distributed like this, what you're really trying to do is you're trying to get those constants, but you're approximating them only asymptotically, right? Because if you're a statistician and you told me, okay, I just care about some like L2 error or something, then I don't really care about convergence and distribution, right? I mean, we can do all this sorts of standard things. So I think it is sort of, the two sides are slightly different in this sense. I mean, they're sort of two fundamentally different goals, I think.
Right, I would agree in general, yeah. These are generally They're both valuable things to study, I think, yes.
So
They're not exactly the
maybe
same.
one sort of point is that often sort of asymptotics and finite sample are like opposed, but in some sense on the right, the way asymptotics is used, it is really a finite sample guarantee. It may not be like the best possible finite sample guarantee, but it's a statement about finite samples.
Sure,
even though
it's
it's what we
just
sort
that
of call
the left side was not derived for that purpose.
Yeah, agreed.
Right? The left side was derived because I'm trying to get a handle of those constants, but I can only approximate them asymptotically, right? I mean, it's if you're talking about just convergence, accuracy of something. I mean, you can do big O, P, all this stuff. It's right. If that makes sense.
There's also kind of a qualitative difference here. It's like on the right side, we like at the end of the day, we just want to say this test works. Well, like on the left side, it's also like, oh, and this statistic will behave as this thing. So for whatever, like if you want to use it for other things, you can also do it. Like typically, if we have a test that works, we don't also give its distribution and technique. Like most of the time, we don't actually know it. So sure, the test works, but if you want to actually do something more qualitative about like, oh, and also it's distributed according to that particular distribution, so I know this thing and I'm gonna like use it somewhere else, typically we don't know how to do that. So it's more, I guess, like weaker in that sense as well.
But more often than not, because there's something really tailored for a particular test or hypothesis. It's not really like.
Sure. Yeah, I think as you can see, this is like an interesting distinction between the two, which we can discuss more of the coffee break. Okay, so I think one last distinction or like maybe terminology thing that I want to point out is sample complexity versus rates. Maybe you've heard both these terms, and they're actually equivalent to each other in the type of statement I'm going to make here today. In the following sense, I'm going to present you a theorem and then like two ways of sort of finishing the sentence. So this is a theorem. I'm not going to prove it for you, but essentially, if you have data which is generated from a Bernoulli distribution with some unknown parameter, we can say that there exists a private algorithm which, with probability 99%, if you take sufficiently many samples, n equals O of 1 over gamma squared plus 1 over epsilon times gamma samples, then we'll have the guarantee that the accuracy is less than, it's accurate up to gamma. But another equivalent way of stating this is kind of the following. For each n, we have that the accuracy is less, the error rather is less than 1 over root n plus 1 over n times epsilon. And you can kind of see that these are two sides of the same coin. If you sort of if you invert one thing, it'll give you the other. I will stick to the first statement, but if you're more comfortable with the second, just know a corresponding statement does exist. Cool. So are there any questions before I go to the first vignette about hypothesis testing? Cool. So hypothesis testing. Hypothesis testing at a high level asks, given some sort of data set X, was it generated from some distribution P which satisfies some hypothesis? This is kind of self-referential, but essentially these are asking yes or no questions about the underlying distribution P which generated the data. And we're going to be concerned with, in particular, testing H0, which is often called or H0, the null hypothesis. In the sense, does this hold? Today we're going to be concerned with the null hypothesis, is the unknown distribution P equal to some known distribution Q, which is the model of interest. So this type of problem goes by many names, including, say, goodness of fit testing or one-sample testing. Computer scientists invented the name identity testing for confusing reasons. But I think it goes by many names, let's say. And in particular today, we're going to focus on the specific problem where Q is equal to the uniform distribution, but pretty much anything I say is going to be more general. So we're going to be considering the uniform distribution over the integers 1 through k. So you can see this instantiated for k equals 10, the uniform distribution. And this is what's known by sometimes statisticians as multinomial data, or the multinomial setting.
One-sample testing means that it's one sample?
Oh, yeah, this has actually confused me a lot when I first heard the term. One-sample testing means the sense that you get data from a distribution P only. as opposed to two-sample testing, where you have data from two different distributions and you want to test if they're the same distribution versus not. So it's not like literally you just get one data point. There's still an n. But this is sort of the problem. And is this clear? Cool. And so our goal in sort of a classical hypothesis testing setup will be the following. If H0, H0 holds, that is, we're actually sampling from the uniform distribution, we want the probability of rejecting to be less than alpha. That is, we want the probability of saying that H0 is false to be less than alpha. This parameter alpha, as has been referred to before, is the significance. It's also known as the false positive rate. And of the two constraints I'm going to mention here is generally the more important constraint and the easier one to control, for reasons we'll get into in a few points. The other goal you have is that if H0 doesn't hold, then we want the probability of not rejecting, that is saying that the null hypothesis does hold, is less than beta. So the parameter 1 minus beta is called the power of the test. That is, alpha is the false positive rate, beta is the false negative rate, and we say a test is perhaps good if it has high power. That is, it's got a low false negative rate. Yes?
How do you quantify it doesn't hold? Like, is it like epsilon far, or because I can get so close to the uniform distribution?
That's a very good question. What if P is very close to, I promise he's not a plant. And often it's what's considered as an alternative hypothesis H1. And so, yeah, often we consider an alternative hypothesis H1, which may be, say, parameterized in some way of being far. But in the asymptotic setting, which is what I'm going to describe in the next few slides, let's just say it's kind of for any distribution which is not H0 in some sense. And one thing that I'll state is that you can often control alpha, but sometimes have to measure beta in the following sense. When H0 holds, then the statistics distribution will be predictable, but may require asymptotic approximations. This sounds kind of vague, but let's go a bit more in depth onto what I mean by that. So let's start with hypothesis testing in the non-private setting, that is looking at Pearson's chi-squared test. And this is the statistic, which is the following. There's a lot of parameters, but let me tell you what all of these things are. We'll walk through this slowly, and then we'll try to understand it. So you can see here, what am I going to say? Q is going to be, again, the uniform distribution over the numbers 1 through k, because that's our model of interest. We want to test if it's equal to that. So in other words, the QIs will be the probabilities of each I, which will be 1 over k, because it's uniform. Ni is going to be the number of occurrences of domain element I. And then we have n being the number of samples. So this simplifies to this or this expression. Sorry, yeah, this is the statistic we're going to be concerned with. And this is just very mathematical, so let me try to interpret this for you as one way of looking at it. Ni is the true number of times we observed domain element I, whereas n times qi is the number of times we'd expect to observe element I. So we're kind of taking the difference between the observed and the expected, and then squaring it and rescaling it. For reasons we'll get into, this will be a natural thing to do, but perhaps it's not the most intuitive. Are there any questions about the statistic before I sort of talk about properties of it? I'll give you an awkwardly long time to parse this. Cool, that was awkward enough. So one theorem is that, this goes back to what I was saying, that in the null hypothesis case, it's easy to understand the distribution in some sense. Because, okay, here's a theorem that you can prove. If the null hypothesis holds, that is, it's actually the uniform distribution, as we take, as the number of samples tends to infinity, then we'll have that this statistic will converge in distribution to the chi-squared distribution with k minus 1 degrees of freedom, where this is perhaps it's the sum of squared Gaussians. If you're familiar with it, great. If not, don't worry too much about it. It's just a probability distribution we know and can understand. And the intuition, again, the intuition behind it is the following. take a look at the observed count minus the expected count and this rescaling, if you sort of squint at it, this looks kind of like the central limit theorem. And this will converge in distribution to a Gaussian with the appropriate, with zero mean and the appropriate variance. And one thing I want to point out is if this converges to a Gaussian, essentially the statistic is a sum of squares of this, thus leading to the chi-squared distribution. It's a bit hand-wavy, but that's roughly where it comes from.
So,
yeah.
Shouldn't we scale by the variance, like nqi times 1 minus qi or something?
It's about, yeah, that would, I mean, if you rescaled by 1 minus qi, I guess that would just make it n01.
Sorry.
Yeah, yeah. So I kind of moved it over to the right for reasons. And the idea is that, so essentially what this theorem says is, again, if you're looking at samples truly from the uniform distribution, then we can predict what the distribution will be of this q squared, except in an asymptotic sense. So we're going to use quantiles of this asymptotic distribution to determine the test outcome. In other words, if we set alpha to be 0.05, we're going to compute the statistic, and if it falls in this tail, it's too large, then perhaps we say, okay, I guess you'd really want some mass here and some mass here. But essentially, if it falls in sort of the red region, you're going to say that this couldn't be the uniform distribution because that was very unlikely. But if it falls anywhere in this white region, then that's okay, that it could possibly be the uniform distribution. And essentially, we say if the statistic is too large, yeah, we output that they're not equal. Alternatively, you might know the term p-value. This is essentially the same thing as the alpha here. And one thing I want to highlight here is that this doesn't, there's two things I want to note here. One, this doesn't account for the asymptotic approximation. We just had an asymptotic result here. And there's no idea of how close it gets for finite samples with this statement as is. And it also doesn't give guarantees about the power, which we'll revisit in a bit. Yeah, Kamath?
It's asymptotic, but it's probably painful and non-optimal to do, but can't we, instead of using the CLT, use some quantitative version of it and get some bound, which is going to give us, as a function of alpha and all the parameters, some non-asymptotic guarantee?
Yeah. I'm sure for this you can derive some non-asymptotic guarantees. This statistic, to the best of my knowledge, is not optimal, though. Yeah, yes, or?
Just a comment that I've looked, and I found one finite sample size complexity bound for this, which is not derived through the nitty-gritty of things in the process of Gaussians.
Okay, so apparently they exist, but they're kind of like not the most common, yeah. Okay, so this is the non-private statistic. Let's look at privatizing, and this is a work by Marco Gaboardi-Lim-Rogers-Vadhan.
You say no guarantees about power.
Okay, perhaps that's yeah. It's not even clear what power should be in the sense that we don't have an alternate hypothesis, so it's perhaps not. Maybe in an asymptotic sense, the power will approach 1 might be something you can derive. I'm not 100% sure.
I think there are statements of the form, if some measure of distance, say chi-squared distance between P and Q is at least
yeah.
something, then you get some alternate sampling distribution, and so that implies some power bound.
Agreed, yeah. I guess
this slide contains no guarantees about power.
Yeah, this slide does not contain any guarantees, and in particular, I didn't specify an alternative hypothesis anyway, so it's not really that. It's not clear what type of guarantees you would even give. Yes, but we'll revisit this, I guess, in a bit.
I mean, I think the most common approach is that basically you do something sort of local. So you say here's like a very small deviation from the null, and then what is the probability that basically I reject? Because you're right, you basically for a fixed alternative the powers will just be 1 asymptotically. But so how do you get some sort of measure? You just let it shrink a little bit.
Right. I guess one way is looking at perturbations of the null hypothesis in some way, and maybe for that family of perturbations you can reason about the null about the power. Yes. Okay, so here is a non-private test. Let's try to privatize it, and perhaps the first way one might try to do this is by noising it appropriately. So I'm going to be presenting some results here by Gaboardi-Lim-Rogers-Vadhan. So the first way you might think of noising it is just to add Gaussian noise to each count, which is, as we know, private. But, and what can we say? As they prove in their paper, it's actually possible to prove that this converges to the same asymptotic distribution, in fact. So if we try to, if we try to follow the same type of analysis, this would suggest we just use the same threshold, but it can be seen that the finite sample significance guarantees are now bad. Let me parse this table for you. So essentially, the way this is done, what we tried to do is set the significance to be, 5% chance of rejecting when we actually have the null hypothesis. And you can see the bottom, let's say the bottom bar is what happens if we just use the same threshold as before. You can see in the high sample case where you have maybe 100,000, is that 100,000 samples, you get something which is pretty close. It has, like, I guess, an 11% chance of rejecting, which is a bit higher. But in, the very finite sample setting, then
very
hyperfinite? No, I think that means something else. Yeah, but in the sort of, say, 10 samples, you get, something that's not meaningful. You essentially reject all of the time. So it's clear that somehow for finite samples, you need to adjust your threshold. Yes, is there a question?
So the distribution in this is still your well-known distribution. This is not the weird non-Gaussian distribution.
Asymptotically, my claim is that it'll be the same distribution if as n goes to infinity, but this causes finite sample guarantees due to the noise.
And in particular, I mean, just knowing what you wrote on the previous slide, this could also happen without the additional noise for privacy, but it happens that the non-private test performs well even with 10 samples.
Right.
Even though in principle the statement that it converges in distribution does not imply that.
Correct. Yeah. So just again to restate what John said, yes, it seems that the asymptotic guarantees were okay in the non-private setting, but when we go to private setting, then something doesn't really work as well as we'd hope. And so there's two possible ways which they explore in this paper, which that figure was also from. One way is use Monte Carlo to determine new thresholds. That is, say, just sample the statistic yourself, like essentially simulate samples from the uniform distribution to see how it behaves, and you can find the right place for the statistic threshold to get the right significance. But you can also analytically understand the distribution for finite n, which takes a bit more work. You now get the significance being accurate. Perhaps the power can be improved. There's other things you can do, like perhaps post-processing. I just wanted to give a shout out to this paper, which has a very surprisingly good method. I enjoyed it a lot, by Dan Kiefer and Ryan Rogers, in which you try to post-project out the noise. But everything I've referred to so far has been sort of non-asymptotic. And the question is, can we rigorously reason about the required size of the data set? And this leads to the definition of minimax hypothesis testing or distribution testing. And here, now we finally, at long last, define an alternative hypothesis, which will be all distributions which are gamma far from the null hypothesis Q. And in particular, we're going to use the L1 distance. So let me sort of parse what this picture looks like for you. So you can see we have the central case here where P is equal to Q. This is the null hypothesis. And then out here, we're going to have the alternate hypothesis where the L1 distance between P and Q is at least gamma. The idea is that we're given the sort of guarantee, the promise that we fall into one of these two cases, and that anywhere in the middle, we don't have to have the accuracy guarantees, sort of as I discussed at the beginning of this talk. Does this make sense? The idea is that, the alternative hypothesis is going to be all distributions which are far, where L1 distance is defined as the following. If you're not familiar, another way of thinking about it is the maximum discrepancy in probability under any event. I guess it's a privacy room. So one way of saying it is the two distributions are 0, gamma, differentially private with respect to each other. I don't usually state it in that way, but maybe for this room I will.
You say TV distance or something?
Yeah, TV distance and statistical distance, L1. These are all total variation. Yes, these are all synonyms, roughly. Okay, and one thing I want to point out is that this is parameterized by gamma. This is sort of in contrast to the previous problems where we sort of focused on, understanding alpha and beta. The reason for this is kind of because I claim that once you get to the sort of alpha or beta equals 0.05 per regime, then you can boost it to any arbitrarily high regime at a logarithmic cost in the domain size, say. But so this is the main thing that we focus on is sort of this parameterization gamma. How big is the distance between the null and the alternative hypothesis in an appropriate distance measure? Okay. So let me show you an optimal, a minimax-optimal non-private test up to constant factors. Then we'll see how we might privatize that. So one test which this was with Acharya and Daskalakis. We showed back a few years ago that this is actually an optimal up to, in the asymptotic minimax optimal sense, an optimal test for testing identity. And one thing I want to point out is this is very similar to Pearson's chi-squared test. The one difference is that you do this minus ni. You essentially subtract out the counts. So this is this kind of weird, and why? It turns out to be the right sort of thing to do in the sense that you can bound the variance, and then doing Chebyshev's allows you to separate the two cases and get a sample complexity bound. But I think it's kind of cool that looking at this from a minimax perspective gave us this tweak which at least theoretically improves the sample complexity. In particular, we can get a sample complexity of the following sort. So let me interpret this for you. Remember the domain size, we're looking at a distribution over the numbers 1 through k. We get a square root of the domain size. This is perhaps surprising in the sense that it is sublinear in the domain size. That is, we don't even need to see all k elements even once before we can tell that it's uniform. And yeah, this was proven, this is the first optimal test that was also proven before. The lower bound is due to Paninsky, and the upper bound is due to Greg and Paul Valiant, who are sons of Les Valiant, if you've been paying attention. So yeah, father in more than one ways. Anyway, so the sample complexity of the problem non-privately is root of this domain size over gamma squared. The natural question here is, how much does privacy cost? And so let's first try to get a baseline for it. I'm not sure, I don't think I have time to go over this in full detail, running a bit short, but there's a framework known as Subsample and Aggregate by Nissim-Raskhodnikova-Smith, which essentially says, split it into different parts and then combine them in some way. There's a very general framework which is used for privatizing normalish statistics, also mentioned yesterday in I think Ilya's talk. But essentially, if you do this type of subsample and aggregate, you're going to get the following sort of baseline for private hypothesis testing. You get the non-private sample complexity with a multiplicative 1 over epsilon, which is already pretty good, to be honest. It's a nice baseline. We didn't have to pay more in the domain size. We didn't have to pay more in terms of gamma. It's a nice place to start, but can we do better?
Sorry.
Yes.
Going back to your original one, your previous slide.
Yep.
So you're saying that the Pearson chi-square is not optimal?
Yeah, I think there is distributions you can construct where under this problem it'll be linear rather than square root.
Okay. 'Cause I thought this was like asymptotically equivalent to a likelihood ratio.
I'd have to think about it a bit more, but I thought we can construct an example like
This might be about the so this is sort of asymptotic as the domain size grows, right? So it may be the case that for every fixed k, chi-squared is converging to the likelihood ratio, but the convergence rate depends on the domain size.
Yeah. We generally picture the domain size as growing to be very large.
Yeah, you're right. So this is, I guess, think of this as a non-parametric test is the right way to.
Okay.
If that's the regime you're in.
So for a fixed k though, then this is not an issue.
Yeah, for a fixed k, then I mean everything is many tests are going to be 1 over gamma squared for like a constant k, so to speak. Okay, so it's actually the issue with the question is whether we can bound the sensitivity of this chi-squared test. I'll point out that the statistic that we used in our that I mentioned a few slides ago, I'm going to just state that the sensitivity is pretty much determined by this n minus this ni minus nqi. That is the true count versus the expected count. And this can be very sensitive if a count is much larger than its expectation. The idea, though, is if something is much larger than its expectation, then it can't be the right distribution. So essentially, using this kind of idea, we first privately check if a count is much larger than its expectation. And if it's not, then we can sort of noisily threshold the chi-squared statistic. That'll give you an algorithm with this sample complexity. This is joint with Brian Tsai and my advisor back in the day, Kostas. Yes. Yeah.
This doesn't look sensitive to me ever, but maybe you mean the square can be sensitive? This is much larger than its expectation?
I mean, consider the case where like all the samples, like the entire data set falls in I, and then the other one has like very small probability, say like QI is 0. So we could have sensitivity of K and, a sensitivity of N rather.
Okay, so
You're looking at how much the square can change, right?
right, so like the square is the thing that's sensitive, not this absolute value. Never mind.
Right. Sort of the bigger this in.
The square is that absolute value.
Yeah.
Up to
It's like the derivative, which is the difference, is the like. Yeah. Is that clear?
Okay, sorry. I thought you meant the sensitivity of like this absolute. Okay.
No. The sensitivity of this is determined by this quantity.
Okay.
Anyway, if you do the calculations for this type of thing, you get something that's somewhat better than before. You still have this root k over gamma squared, but now the additional cost is sort of less in some. It's sort of free in certain regimes. This is one sample complexity. You can actually do even better. It turns out, like, you might think that this is not a good statistic because of the fact that it could vary so much because it has a square. It turns out there's a few better statistics that are better for this sort of thing. For example, one statistic that works and is optimal for this problem in a certain regime is counting the number of things you don't see. That'll give you something that you can privatize, which was done by Aliak, Bauerpour, Diakonikolas, and Rubenfeld. And a bit surprising to me, Diakonikolas et al. Also showed that empirical L1 distance, which is a very insensitive statistic, can also be privatized. Or sorry, that this, first of all, this algorithm works non-privately and is very insensitive, so you can privatize it as well. And if you do the calculations, you're going to get something that looks like this. So I think this is kind of interesting. This is the optimal sample complexity. We have this first term as before, and then a slew of other terms, which I'm not going to read out for you because that'll take like a long time to get all those exponents.
But each of which is known to be
yes.
necessary.
There are lower bounds in Acharya-Zhang, which shows that this is tight. So I think it's kind of interesting how, this was the non-private complexity, and once it becomes private, we have 3 new terms, each of which is the dominating term in some regime. Yes?
Just a small question. Is there a principled approach of like how to come up with these optimal tests? Like, why do you choose a specific form? I mean, it seems like for the non-private version of this problem, it seems like the optimal test is not unique. Like,
yeah.
If you discard constants.
Yes.
So how would you come up with that? Is there an intuition behind this form of the test?
I guess one intuition is that, like, sort of in one sentence.
The TV distance, the total variation?
Well, one observation is that for a uniform distance, TV is kind of, you can sort of estimate it by looking at the number of collisions. And chi-squared can be seen as a way of rescaling it so that's kind of uniform-ish. And then looking at the L2. But this is probably, I'm happy to talk about this more offline. Are there any questions about hypothesis testing before we move on? Cool. The next main vignette I'll try to get into in the last, say, 10 minutes or so will be distribution estimation, which is, as you might expect, given n samples from a distribution, privately estimate the distribution. The main thing that I didn't say here is, what is this distance? We want to approximate the unknown distribution in some sense, but the choice of distance is somehow unspecified in this statement itself, and is actually really important, as we'll see in a number of results here that I'll mention, that the cost of privacy can vary wildly depending on the distance.
Yes. So I guess this choice of distance would matter also in your previous questions. Has this been looked at under other measures?
Indeed. There's been a good amount of work on understanding in a non-private setting, but I'd say not yet in the private setting. It's a good question, though. Okay, let's see what we can do with univariate learning that are just one-dimensional problems. First off, since we've been working with multinomials, let's see about privately estimating a discrete distribution over 1 through k. And it's pretty much, it's a folklore result that just by noising the empirical histogram, you can get essentially the domain size over over gamma squared, which is the non-private complexity, plus k over gamma times epsilon. So essentially no additional cost in the domain size and minimal cost in terms of privacy. You can see this calculation, for example, in a work by Ilias, Moritz, and Ludwig. But the point I'm trying to get across here is that the cost of privacy is really minimal in the sense it's nothing changed too much. I consider this to be a minimal increase. However, an interesting result is showing that in Kolmogorov distance, which is a picture that looks something like this, the distance in the CDFs, this is a very easy distance to estimate in non-private settings in the sense that you can just get 1 over gamma squared, which is independent of the domain size. But oddly, due to this result by Weimel, Nissim, and Stemmer, you get this additional additive 2 to the O of log star k over gamma times epsilon, which is like a very, very small term if you're not familiar with log star. And this is actually tight. All right. Not tight in the sense that like up to constant fact. Yeah, the lower bound and upper bound are indeed exponentially off, but these are like both incredibly tiny things. So this is a bit, I don't know how to really quantify this, in the sense that this is actually indeed a very expensive cost in the sense that before there was no cost in the domain size, and now you have one, even if it's minuscule. So this is like a qualitative shift in the complexity, which I think is very interesting. Okay. So another oh, sure.
So Kolmogorov here distances. So I imagine the integers are ordered, and I really want the. I'm just sort of translating this in my head from the version of these statements that I'm used to writing down. And yes, okay, yes. All right, I get it. I'm good. Thanks.
Cool. This works also for continuous distributions in the non-private case?
Yeah, that's perhaps the most like interesting part, the fact that even for continuous distributions you can approximate in Kolmogorov, but you can't in the private setting.
Yeah.
Okay. So also what about Gaussians? I guess Sasha talked a bit about this before, but essentially a result by Gaboardi-Lim-Rogers-Vadhan shows that the sample complexity is this expression here. And you can see that the leading term is still 1 over gamma squared, which is the non-private complexity. But now we have interesting new terms here, which sort of depend on the scale and the position and the range of the data. In the sense, we really need bounds on the domains, on how big the mean and the variance are now. And this lets us estimate an L1 distance. I won't get too much into this. But the cost of privacy here is really mild in terms of the scale parameters, but it's now, again, like before, something that wasn't there before, but now we've introduced it due to privacy. I'm going to mention multivariate learning, product distributions. In the sense now, suppose we have a multivariate distribution. We want to privately estimate the mean of this distribution, and we're going to focus on like binary product distributions. Here's the case with d equals 3. And in this case, I'll actually demonstrate how the choice of the distance in which you want to estimate the mean can change the sample complexity a lot. So first off, if you just want to estimate an L2 distance, this turns out this is just the univariate algorithm, Laplace each thing independently. You get this result here, which essentially says that privacy comes at minimal cost. And actually, if you want to learn the distribution in L1 distance, then a recent result with Jerry Lee, Vikrant Singhal, and John Ullman shows that, in fact, in this sort of stricter distance measure, then we can also estimate it at sort of no additional cost. However, if instead you were concerned with, say, L infinity distance, you want to estimate the mean up to L infinity distance, now we can see something sort of a new cost arising in the following sense. Non-privately, you'd have to pay the log of the dimension, but with privacy, now you have the square root of the dimension. So in other words, you had to pay an exponential cost in the dimension in order to get privacy. So it seems like there's a big difference here. Let me just spend 1 minute saying why we might consider an L-infinity distance in a phrasing that might make sense more to you. Suppose we asked a set, we were asking a population of people d different questions, and they gave us binary answers to all d questions, and we wanted to estimate each answer of the belonging to the underlying population up to an additive, say, gamma, then L-infinity distance is essentially what we'd be estimating the mean to. So this is a very natural notion of estimating the mean, but it seems like this one you have to pay a lot more. Are there any questions about this slide?
This is chi-squared distance on the vectors of means, not
yes.
the distribution.
Correct. So this is estimating the mean of the distribution in chi-squared distance, which corresponds to learning the distribution itself in L1. Otherwise, it'd be like, why are we looking at this? But this is the one that seems to characterize it.
The last one is for epsilon delta, or?
Yes. Yes. Sorry, yeah, that should have been. Okay, and we also have corresponding, there's a one-dimensional problem which Vishesh and Salil studied with John, Jerry, and Vikrant as well. We studied a high-dimensional version which roughly has the same story in the sense we can pay a mild dependence on the scale parameters. But again, this is interesting compared to the L-infinity statement where you really had to pay an exponential cost. Okay, I had some slides on distribution learning versus reconstruction. I'm kind of running out of time, so we can talk about this more offline and why, reconstruction attacks don't really give good private learning lower bounds. Also, distribution learning versus linear queries. They're kind of different questions in the sense that one, we learn all queries but for a simple class. The other one, you learn some queries but for a complex class. Again, happy to talk about this more offline. Should I? 5 minutes? Okay, sure. There's other problems we could also consider, such as things like distributional functional estimation, where we're trying to privately estimate some function of the underlying distribution. Things which have been studied a lot in the TCS community include things like support size, distance to uniformity, or entropy, under sort of the title that you might have heard by Greg and Paul Valiant, Estimating the Unseen. And the interesting thing in this case is that these require, say, one interesting case that I want to point out here is the fact that these are known to be generally expensive properties in the sense that if you consider K being the domain size which is large, you have to pay something which is almost linear in it. But interestingly, we managed to show that you can get an additive cost which is sort of a lower order term in this sort of high large domain setting. So this is one place where I consider the cost of privacy to be somewhat negligible. Hypothesis testing. Let me just quickly state some results. Another related question to hypothesis testing as before was instead of trying to do, is it to say one distribution or something far from it, there's what's known as simple hypothesis testing, in which we either know it's some null hypothesis or some particular alternative hypothesis. That is, it's either one distribution or the other. And this is a very well understood problem in classical statistics in the sense that there's what's known as the log likelihood ratio test, which looks at this quantity here, which I won't parse for you. But the Neyman-Pearson lemma, one of the most classical results here, says that this log likelihood ratio test is optimal. That is like no constant factors, like this is the best test that you can get. It's uniformly, it's the best test. So in case you like minimax bounds, you can actually show that the sample complexity of this test for any two hypotheses, Q0 and Q1, is going to be 1 over their Hellinger squared distance, which is another type of distance. And so this is a kind of very nice, story to tell about this one test. The issue is how to privatize, in the sense that privacy, as I mentioned before, is related to the sensitivity of the statistic. And in particular, if you have one place where one PDF is very large and one is 0 or small or even 0, then you can see that this log likelihood ratio test could be very, very sensitive. So the question is, how can you really privatize it if you're looking at a very sensitive statistic? And it turns out that a test that's kind of like this works. Now, let me explain a bit of notation. This sort of parentheses notation means that we cap it to this range, in the sense that if it's bigger than epsilon, then we round the statistic down to epsilon. And if it's smaller than minus epsilon prime, we're going to round it up to minus epsilon prime. Once you do that, you can see that the sort of statistic is bounded, of bounded sensitivity, and then you can add Laplace noise. Very simple statistic, right? There's something I'm hiding here, and the fact that I said epsilon prime, and I didn't state it. And if I wanted to state it, this would probably, even just to state like the result, I think would be at least another couple slides. And it's a very complicated measure of distance now. But the point is, this epsilon prime is actually quite a tough problem, tough quantity even to define. So the main thing I want to get across here is that simple hypothesis testing, while it was very easily and well understood in the non-private case, it becomes much more complicated here. And this is a result with Clement Cannon, Audra McMillan, Adam Smith, and John Ullman. So this is not quite Neyman Pearson in the sense that it's not as clean and neat as we would like. It's not optimal up to constants, optimal up to constants, but not optimal exactly. So I feel like there might be something better here, but it becomes just too complicated to understand. And I'll say that for certain cases, we can get uniformly most powerful tests, which Sesha mentioned a bit before, but they can't be done in general due to Brenner and Nissim. This type of thing can be used for change point detection. Let me skip this. Other things. There's other things I did not get a chance to mention today are things like local privacy. There's been a lot of work, but of course I'm already over time, so this would have been a fool's errand to try to cover all of these in detail. And also there's other related tasks which could be generally considered as statistical tasks, including PCA clustering and how to compute robust statistics, which are other things which I'll put these slides online so you can peruse all of these if you'd like. Anyway, thank you.
One question and then take the rest into the break.
Sorry.
Yeah.
There's no one.
Yes.
So in most of the slides you show that you look at what you would normally do, or the optimal thing you would do non-privately, and then think of some noise addition based on sensitivity. Is there I would say, more systematic way to approach the problem under privacy by looking, for example, at, another way to phrase my question is is this always optimal? Maybe the statistic that was optimal non-privately is no longer optimal, and maybe you can think of something else.
Yeah.
Based on some modified version of log likelihood or something, but under privacy.
I guess that's a good question. I guess I'd say that, in general, if you want to get the non-private optimal term, you kind of need it to be optimal in the non-private setting as well. But the idea is there may be multiple tests, as we sort of saw for, say, identity or goodness of fit testing, and choosing the right one, they might be amenable to privatizing in different ways. So it's kind of, I don't think I personally have a theory of this yet, and I'm not sure if anyone does, but I think that's a very good question, trying to understand which families of statistics may be more easily privatizable. Yes?
It's a quick question, we can take it, otherwise can we maybe go into the break?
I can ask it anyway.
All right, well, let's thank Gautam again.